Hello and welcome everyone to this video on the basics of speed control in an electric drive or variable frequency drive. If you aspire to be technically sound in industrial drives, or if you want to understand the reason behind drive faults due to speed control or whatsoever be the reason, or if you have faced situations where you are not able to understand how do the controls of a drive works, this video is going to be really helpful for you. And if you want to prove your mettle in the field of automation and drives, this video is specially for you. So today, my friends, I'm going to show you the logic that forms the core or the brain of the drive. I will show you a logical representation of the program that runs inside the CPU of the drive. If you are a drives engineer or someone who has worked with drives, you will know that we always set parameters called as drive parameters, which governs the controls of the drives, right? But have you ever thought after you enter those parameters, how does the drive process that information? Have you ever thought when you change the speed reference, how does the drive go about meeting that speed, or how does the drive help the motor to achieve that speed? Or very simply put, how can you tune the drive to achieve the best speed performance? Right? So by the end of the video, my friends, you will have an answer to all these questions. And yes, please don't forget to subscribe to this channel to get regular updates. Let's get started with the very basics. So broadly, there are two types of control modes in any drives. So one is speed control and the second is torque control. In basic understanding, speed control means you will be giving a speed reference to the drive, and the drive will meet that particular speed reference. And whatever torque it needs to achieve that particular speed, the drive will take that torque within the limits that has been set in the drive. This is what the speed control means. However, we'll look into more details, but just briefly speaking, this is what is speed control, and torque control means you are passing a torque reference to the drive, and the motor or the drive will try to meet that particular torque reference irrespective of what the speed is. So these are the fundamental two differences between speed control and torque control. I'll repeat for clarity. In speed control, you pass the speed as a reference and the drive will meet that speed that you have passed. In torque control, you give torque as a reference to the drive, and drive will achieve that torque value whatever you have passed. So in this particular video, we will try to understand in detail how the speed control of a drive works. Now there are two major parts to it. One is how the actual speed comes into the drive, and the other part is how the reference speed is generated for the drive. So one by one, we will understand both these broad buckets, and then we will understand how the difference between actual and reference speed is met. So actual speed, as you might already know, encoder is an instrument which is installed in the motor, and this gives out the pulses uh, according to the speed of according to the actual speed of the motor. As you see here, the encoder signals, which are digital pulses, goes to a pulse encoder module. Now this is a hardware module which converts the signals and sends it to the drive. And in this, and then there is a block called as encoder speed calculation. Here you enter parameters such as what is the PPR, pulses per revolution of a motor, and other factors such as scaling factors. So what this block essentially does, it converts the pulses received from this encoder into speed measured, which is the RPM. All right. So whatever is the encoder speed in RPM, you will be getting as a part of a parameter. Now, whatever parameter here you see in red, bold red, are the parameters which can be read in the drive, while the green boxes, the green background parameters that you see, these are the parameters for which you can set a value, or which for which the user can set a value in the drive. So, and this particular block is a selector block. So So there are two inputs. Either of these inputs can be selected based on what is the signal being received. So this is a control signal. Now then here is a parameter speed feedback select. This selects the speed feedback value used in speed control. Why is this going into this block? This block is encoder signal faulty logic. So if suppose uh, this particular encoder starts giving a faulty value, you don't want that to go into the drive for processing, right? So even if the speed feedback select is encoder, this will not allow this value to go here in case the signal is faulty, right? So this is a safety aspect. But yes, if the signal coming is healthy and if the speed feedback select is set as encoder, then the speed measured RPM goes further into the logic. If speed feedback select, so there are two options for the parameter of speed feedback select. In case of ABB drives, generally ACS 800 ones, the two options are either encoder or the interval one. So if you take the second option, the speed which will be passed is a speed estimated, which comes from the motor model. This is a calculated speed based on the motor model and the different parameters of the drive that is there. So this motor model is calculated when you ID run the drive. That is the first step when you do the commissioning. So now this actual speed goes into a filter. Why is this filter is used? Because you don't want the fluctuations in the speed to impact your control logics. Hence a small amount of filter is used, and then you can select this parameter speed actual filter time. The more timing you set, the more smoothened the curve will become. But then you cannot set it really high. You cannot set it as something like a 5 second or 6 seconds as speed actual filter time, because that also adds a lag. If suppose there is a spike in the speed of, let's say it it rises from 50 rpm to 100 rpm, you will feel the impact here after 5 seconds if you set the speed actual filter time as 5 seconds. Hence, generally that high of a filter time is not used. Generally 1 second of filter time is more than enough. We generally, in my experience, I have only used this filter time of 200 milliseconds or 400 milliseconds to the max. And then there are also some safety controls. As you see, this speed which is received from the encoder goes into a speed monitoring logic block. And then again, there is a parameter where you set the speed limit. If you start receiving a speed from the encoder which is higher the speed, the drive generates an alarm or a fault, which says that the speed that you're receiving is above limit. All right, so this is the entire logic of the actual speed. So the final output is the actual speed or the motor speed parameter. Now this motor speed parameter can be read at any point of time. And in case of ABB ACS 800, this parameter is parameter number 1.04, and the speed measured is parameter number 1.03. So at any point of time you want to see what is the final value coming here at motor speed, you might want to go and check the parameter number 1.04. Or if you want to check what is the value of speed coming from the encoder, you can go and check the parameter number 1.03. And in fact, as this is a step generally taken during commissioning. So when the motor is rotating in the correct direction and the speed reference is positive, so this actual speed, right, which is the speed measured, must be positive. So there should not be a significant difference between the estimated speed and the actual speed measured, which is coming from the encoder, if all the parameters have been set correctly. Now let us understand what are the logics inside a drive for reference speed. So the block that you see is a selector block, speed reference selector logic, and there are two inputs coming into this. One is speed reference from automation, which can be any of the standard field bus protocols, like be it Modbus, Profibus, or whatsoever. And another option is IO speed reference. So you can also interface a 4 to 20 milliamp hardwired signal And then you can set a parameter, this parameter communication module. Based on this parameter, what you set the signal which you want goes further for speed reference calculation. So in case of ABB drives, this communication module is parameter number 98.02. So just please note that whenever I say ABB drives, it's ABB ACS 800 series or 880 series drives. Now, based on the selection of the parameter that is set in the communication module, the speed reference gets selected and is passed forward. Now, this speed reference parameter that you see here, in case you want to check for ABB drive what is the speed reference, you can always check the parameter number 23.01. Now this again goes into a selector block. Now here there are two options. One is either you can take the speed reference that is being received from automation. Also you can have a local speed reference, which is the speed reference that you can set directly in drive. So in applications where you don't have a PLC, you have only a drive to control a motor, or in a pump applications, you will always have this local control parameter set. And if this local parameter is on, then local speed reference goes further, right? But for our further explanation, we will always consider that there is a PLC and speed reference is being received from a PLC. Now this goes further as used speed reference, and then there is again a limiter block in which you can set parameters for minimum speed and maximum speed. You set the speed; these are the limits that you want to set. You would never want to set a reference speed which is more than the rated speed of motor. So let's say if the motor is rated at 1050 rpm, your maximum speed has to be 1040 rpm. You don't want to run the motor beyond that because it's a safety feature. You might have motor burn if you try to run it at a higher speed than the rated speed. So after this limiter block, the speed reference moves forward, which I have named it as speed reference 2. Now this again goes in an acceleration deceleration block. Now this is a very important block. The two most important parameters to set for this block in a drive is the acceleration time and deceleration time. There can be other parameters also for this block, but these two are the most important ones. Now what it does is you you never pass a step change in the speed reference to a drive. It always has to be a ramp so that the drive can smoothly catch up the actual speed, or the change in speed to the motor is very smooth and there are no spikes in torque. And if there is a step change in the reference speed, your motor will always try to react to that step change, and there will be a jerk in the motor that can also result in damage of the bearings or any other components in the motor. And it is very important to tune this acceleration and deceleration parameters. Now, what does this acceleration time mean? So this is the time duration in which you want the speed to rise from 0 to a maximum speed. Again, deceleration time is the time time of the entire duration of the slope which you want for the reference to come from the maximum speed to a 0 value. And in case of ABB drives, this acceleration time is parameter number 22.01, and this deceleration time is 22.02. So now you have two primary signals generated, which is the actual motor speed and what is this reference. So this gets subtracted and the resultant is moved into a PID controller block. Now this is the most important part of the entire speed control loop. And so what is a PID controller? So it stands for proportional, integral, and derivative controller. As you know, works on the principle of a control loop feedback mechanism to control process variables. And these are the most accurate and stable control mechanisms. So this has three parts. As you see here, P stands for proportional, I for integral, D for differential. Now we call this difference as the error signal. The difference between the reference speed and the actual speed is the error signal. Now this error signal gets fed into the controller and accordingly gets multiplied with these components. So the entire function is quite long. Just to keep it simple, I would like to, I would only say that the error gets multiplied by kp, ki, and kd. So it would be like error into kp, and for the integral part, plus ki into the integral of the error, plus kd into the derivative of the error. And as a part of tuning the controller, you can choose whether you want to use all these three parts or only kp or any combination of these. But for 95% of the practical purposes, only p part of the controller is used. I'll explain why you don't need to use I and D part, but yes, mostly only kp is used. So in control systems terminology, these are also, this kp, ki, kd are known as the gains of the controller. So kp is the proportional gain, ki is the integral gain, and kd is the differential gain. Now kp, or the proportional gain, means kp is multiplied with the error signal to generate the output of this controller. Now this component of the controller helps to eliminate the error signal. We'll try to make this error as 0. Again, ki is the integral gain, which means that ki gets multiplied with the integral of the error. So in this figure, if you see, it's just an illustration of what integral means. So this straight line that you see, let's suppose this is the reference and this is actual. So if your actual rises beyond the reference, so over time this gets integrated. So this entire area, which is 135, is the integral sum. So this 135 will be multiplied with the ki, and the output will be generated, and hence this speed will come down, and again the next time the integral sum will be 34, and again the differential gain gets multiplied with the differential of the error signal to generate the output. This part of the controller helps to improve the transient response of the controller. Transient means the time the signal takes to settle to a steady state. So this is the transient time in which it is fluctuating like a sinusoid, and once this reference meets actual, this is the steady state. So the timing at which it takes to meet this steady state is called the transient timing, and KD helps to reduce that time. And when you are setting these parameters in the drive, KP, KI, KD, you can assign 0 to the parameter you don't want to use. And as I said, for most of the applications, only KP is used. KI, KD values are 0. And I would also recommend to keep these values as 0, except for some special applications. Now, if I tell you the reason why only KP is used, it's because you want the speed control to be very smooth. Generally, in applications or in the process side, you don't want any jerk in the motor output. So, if suppose, let's say you have activated the KI part, your integral sum becomes quite high, and hence this output value is high, and this generates a jerk in the motor. So to keep the response as very smooth, only KP is used, and this meets most of the requirements. So this controller output is generated as a additional torque reference. Now suppose your actual speed is more than the reference speed. So in that case, you would want your torque to be negative because you want to bring down the actual speed. Now let's say you are accelerating. So in that case, your reference speed will be higher than actual speed. And then this will generate a positive torque reference, which will tell the motor to raise the torque, and that torque will be used to increase the speed until the difference between actual and reference goes to 0, or at least near 0. Now let us understand how do you set an optimum value of this KP. This is the most important part of tuning a speed control of a drive. What value of KP to set? Now, in the first figure, as you see, the dotted line is the reference speed. So let's say you have a 0 value, and then you have given us speed reference of, let's say, 200 RPM, right? So this is the step of 200 RPM. So the actual line, the solid line that you see, that is the actual speed. So in some time, this actual speed meets the reference speed. But then there has been quite enough of time gap. It has taken quite some time to meet the reference speed, which might not meet the process requirements. Hence, the KP value is too low. You might want to increase the KP value. Now, the second graph that you see, this is an example of what will happen when your KP value is too high. Because you have generated a very high, this differential torque will be quite high because your KP is high, right? So the additional torque will lead to some overshoot of the actual speed beyond the reference. And then the torque reference swings. So this is also a condition which you would want to avoid. So this is an example of having a high value of KP. And this graph is somewhat looks like the most optimum value of KP. You have given a reference, and within no time the actual has met the reference. So you want your response to be something like this for a correct value of KP. And in my experience, most of the times KP is value has been somewhere around zero point 0.6 to zero point 0.9, or in rare cases 1 as well, but not more than that. But it depends from manufacturer to manufacturer also. Now this torque reference 2 gets passed on here. So to a torque selector. So here we have two references, torque reference 2, which is from speed controller that we saw in the earlier section, and this is torque reference 1. So if you remember what I had told about the torque control mode, in case of torque control mode, the drive gets a direct torque reference from either PLC or from another drive, or from, it can be from a analog input as well. So that forms torque reference 1. So you can select this torque selector parameter to choose what kind of a mode you want to run in. So this gets passed on as torque reference 3. And then in case of ABB drives, you have a parameter called as load compensation. And this, there is an addition block. The torque reference gets added to the load compensation and gets passed on as a final torque reference, which is torque reference 4. Now, why this load compensation is used? So, in applications where you have a lot of weight added to the motor, so let's say in the case of rolling a steel coil, the coil has a lot of weight, and when you are accelerating or decelerating the motor, you want to compensate for the additional weight. So that is something that is sent from the automation as load compensation. So this is the amount of torque which is required to overcome the inertia of the motor, because your motor in most of the cases will be coupled to a gearbox and some additional load as well. So you would want to compensate for that additional losses that are incurred in the to meet those inertia of the additional load. So that is load compensation. So this torque reference which is generated from the speed controller, which will will be only a result of the additional speed that you want to run. Just to keep it simple, just understand that you get the torque reference 2, and then you have the final torque reference 4, which goes into a series of limiting blocks. Now, all these are safety limits for the drive and is based on the ratings of the drive and the motor. So the first safety block is the frequency limiter, where you can set the frequency maximum and frequency minimum as per the rating of the inverters. And then you also can set a frequency trip margin. So when the drive output exceeds this trip margin that you have set, example, in the case of overshooting of speed control, if there is an overshoot, the drive will be stopped with a over frequency fault. So this generates a torque reference after frequency limiter, making sure with respect to this torque you, so that you don't cross or don't bypass the frequency levels that are being set for the drive. Again, the next block is a DC voltage limiter block. This makes sure that your torque is in accordance with the DC voltage ratings of the inverter. And then you generate a torque reference after voltage limiter block. Then you have a final block, which is torque limit calculation. Here your current levels are checked with respect to the maximum current and of the motor, and what is the inverter maximum current. If supposed to meet the torque reference, it calculates the drive calculates the current to be going higher than the maximum current. It will generate accordingly a, a current limit fault or a trip, whatever you can configure it to be. So there are two fault signals here. Important. These are some of the most important fault signals. If the current crosses the maximum current level, it will generate a torque motor current limit fault. And in case of breaching of inverter maximum current, it will generate a torque inverter current limit. Now this final is the torque used reference, which goes into the control block of the drive. So most of the drives offer two types of controls, which is scalar or vector control, and accordingly the switching signals are passed onto the inverter. So these are the switching signals for the IGBTs which are housed inside the drive, and accordingly it changes. So whatever are the voltage and frequency calculations, accordingly the signals are being sent to inverter, which is then fed into the motor. So this is the entire control logic that runs inside your drive. Now I will explain you all this with an example. Now I will explain how the entire speed control logic works. So this is a software which is used for the acquisition of all the signals in the drive, and I have plotted all these gets plotted automatically in this analyzer. So what we have here is speed reference, the blue line, the reference which is passed, and then the actual speed in RPM. And then we have torque reference 4, as I explained in the earlier block diagram. And then we have the actual torque of the motor, right? So we'll see how all these four signals changes, because just summarizing the entire control logic loop of the speed, as you increase the speed reference, the torque reference increases. Now this increases because of the proportional controller. So here in our case, we have only activated the proportional controller, not the integral and the differential one. That generates an additional torque reference 2, which gets summed up, and the final reference goes on as torque reference 4, and that reference is sent to the vector control block, which passes the switching signals to the inverter, and which runs the motor. And finally, you get the actual torque. This is just to verify that my actual is meeting my reference, and the speed reference is meeting my actual. And because this is in speed control mode, the priority is to meet the speed reference and speed actual. So if you see here, the motor has been running at 50 RPM. The reference has been changed to 100 RPM. Now this takes some ramp time. This is where the acceleration time and deceleration time comes into picture. The reference speed increases, and as the reference speed increases, you see the torque reference starts increasing. And as the torque reference starts increasing, the actual also goes high. Now this actual signal is a filtered one. That is why you see some amount of lag, but in actual this must be a few some milliseconds before time. So as you see, to reach this 100, the torque has gone up and the motor is able to meet this reference speed. And you see there is no overshoot in the signal, right? If you just take a closer look, the actual signal meets the speed reference. There is no overshoot of the signal. And if you want to see how much is the time needed to meet, I'll just change the markers. X2 minus X1, this is the time. This is 0.889 seconds. This means only 889 milliseconds. Within 889 milliseconds, my reference has changed and actual has also very accurately followed. I'll zoom out a bit. So these are further step changes. So after 100 RPM, the speed was made as 300 RPM. And as you can see here, accordingly, the torque reference has increased and so has the actual to meet this additional. Now there is a lot of additional load which is coupled with the motor, hence this reference has gone high. And again, it has come back to a normal torque for operating at a steady speed. Now guess what would happen when we are decelerating the motor. So similar is the case for all these step changes. It would be interesting to see what happens during deceleration. Now see here, the motor was running at a speed of, check the marker, at 1400 RPM, and from 1400 the speed reference has been changed to 214 RPM, right? And you see this is a smooth ramp, and what has happened? The torque reference has gone negative. Why the negative torque? Because the force is to be applied in a reverse direction. There is a heavy load which is connected to the motor, and there is a lot of inertia with which the motor is running at a speed of 1400 RPM. So in order to make uh, this actual speed follow the speed reference, or to decelerate it smoothly, you need to apply force in a reverse direction so that this actual speed does not overshoot because of the inertia. Hence, the torque has been applied in a negative direction, and the actual has also followed the torque, and the motor meets the reference speed almost at all the times. So I hope this makes it very clear how how the speed control of a motor works, and how does a drive control the speed of a motor. This, if you have any questions, please feel free to comment it out in the below comment box. Also, please don't forget to like the video and also subscribe to my channel. Thank you very much.